So x pi a is less than ya for some a which is less than or equal to 1, or rather that's in between 1 and n, and also that y, let's say pi prime a is less than za, again a is between 1 and n. And in other words, there's a permutation where some element in x is less than ya, and mind you, the ya is ordered, but in here there's a different permutation y sub pi prime a that's less than another set of elements for each some element z. So the implication is that, of course, x is nested in y and y is nested in z, and we have to prove that that indicates that x is also nested in z. And so basically we can find a third permutation, because for every x pi a there is basically a ya, such that there exists z, some element in z where y is less than z. So in other words, let's say there exists ya such that there exists a z b, again for a b between 1 and n, where ya is less than zb. And so ya is in some permutation pi prime. Since this is true, in other words, we can find a ya and pair it with a zb because ya is nested in there. That means we can also find a xa, or x within the set of x, and pair it with a y so that we can satisfy this, and then by transitivity of inequality we can prove that x sub c is less than z sub b for any x sub c inside the set x, right? The permutation. So we make a new permutation, let's say pi, ooh, that's terrible, 3, I'm still getting used to this, pi 3, composed of an x sub c selected so that we find a y that is less than it, which is less than some z. These are values, as abstract as they describe them, they're values. So of course that's implied in the fact that there's an inequality. And so what we can do is say we're given sets x and y, so we can sort x and y, both of them. This takes, in terms of n and d, well, there will be d elements, log d. And so now we have these two sorted sets. And in the same way, you can kind of realize that this works because of the same argument we use in transitivity, which is that we can find an x that is less than some y. If we can't find that, then it doesn't nest. So we can sort these two and then iterate through them so that we find an x that is less than every y. So we can say for I equals 1 to d, and we pair xi with yi. If xi is less than yi, and if not, we just return false to bn. So it's composed of boxes, and remember these have d dimensions each. So what we're going to do first is say, well, for every box inside the set, we're going to sort B. So this is our first step. And since the size of B is D, there's D dimensions, and the size of SB is N, basically we're sorting N times, and it takes D log D to sort. So this costs D ND log D. And remember that S sub B is a set of sets. So we have to create a graph for this. What we're going to do is define a graph, and we'll say this is not strict syntax really, but we'll say that we'll say V, and we'll define V as let's say V sub B and then we union this with, let's call it VS starting and VE for ending. And I'll explain why we need that in a second. So what we have basically is we're going to make a vertex for every box. So a vertex is going to represent a box, and then we add 2 extra vertices to that. And then we'll have a set of edges. So let's say that our edges, let's define them as, firstly, UV and we'll just say that the weight is 1. This can be a constant. I mean, it doesn't really matter. All of the edges have the same weight, and I'll explain why. Well, it has to be weighted for a few reasons, I'll explain in a second, such that there exists, say, B U and BV, and BU is nested in BV, where BU, BV are inside SB. So they're elements of SB. So this is their first set. So in other words, we make an edge from the vertex U to the vertex V if, of course, if the 2 boxes exist and box U is nested inside. We'll say that we're using this to say nesting. So BU has to be nested inside BV. So if vertex U, its box is nested inside V, we make an edge, and we make a union again, and this is going to be, let's say, well, we named it VS, so VS cross this same set VB, where B is inside SB. In other words, the same set of vertices that we just made, and we have a weight of 0, or I should kind of point out here a weight of 0. Okay. And we also are going to union this with VE, VE cross, again I'm being a little sloppy here with the expression, but the same set. With weight equals 0. So basically what this means is that we have edges from U to V if box U is nested inside box V, and then for every vertex that represents a box, we're going to make an edge from the starting vertex to that vertex. So basically, let's say you have 2 boxes, and this is the starting point. Every box is going to have an edge pointing to it from the starting point, and also, that was kind of my fault. I should switch these over because this is the other end, so it's actually supposed to be switched over, and V is supposed to be here. But anyway, point being, we have VE here, and this is VS. So in order to make this work, the reason why we have to have the beginning and ending vertices is because maybe you'll have something like this, where you have pairs of boxes that are disconnected from one another because they don't nest within each other, or you'll have somewhere along the line it'll be disconnected and you'll have a disconnected graph. So we want to have these so we can point to every spot and begin there in order to see if we can get the longest path from that. Another thing is that we want it weighted because in a general graph this would be NP hard, finding the longest path, but this is a directed acyclic graph, luckily for us, so this can be calculated actually in V plus E time. Right, the size of V plus the size of E, and in our case V does not dominate because it's just big O of n, but E there's n squared because we can have an edge from a box to every other box for each box, so that would be quadratic. And so in order to construct the graph, then we make vertices, and each vertex, well, there's one for each element in S sub B, and that's n, so this is big O of n that does not dominate. And this Cartesian product with the starting vertex and every box vertex, that's again big O of n because this set size is 1 and this set size is n. And the same thing for the ending vertex crossed with every other vertex except for the beginning one. Those are both big O of n. That does not dominate. But we haven't solved or stated how we are even calculating how BU is nested inside BV. And remember, we sorted before we started all this construction, so now we can, in every single box, we can ask the question of whether it's nested in linear time, right? But we have to do this making an edge from one box to every other box for each box. So that's big O of n squared, and it takes d time in order to determine if it's nested. So for each box, we look at every other box and see if we can nest one in the other, excluding, of course, there's a kind of a hidden value here that's not that doesn't dominate because we don't direct a vertex to itself. But the point being, it's n squared d. And then if you want to get a little bit more descriptive, well, it takes nd log d in order to sort. And so this is what you have for the worst case complexity.